Analyze the thermodynamic favorability of the reaction. The standard Gibbs free energy change for the conversion of diamond to graphite is given as delta G degrees equals minus 2.9 kilojoules per mole of reaction. Because the value of delta G degrees is negative, the reaction is thermodynamically favorable, spontaneous, at room temperature. Distinguish between thermodynamics and kinetics. Thermodynamic versus kinetic control. Thermodynamics dictates the ultimate favorability and equilibrium position of a reaction, but the value of delta G degrees does not indicate or influence the rate, speed, of a reaction. The rate of a chemical process is a kinetic property governed entirely by the reaction pathway and its activation energy barrier. Examine the chemical structure of the reactant. Diamond is a covalent network solid featuring carbon atoms that are held together by exceptionally strong covalent bonds extending in 4 different directions to form a rigid, 3-dimensional tetrahedral lattice. Relate molecular structure to activation energy. Converting diamond into graphite requires breaking these highly stable carbon-carbon bonds within the network lattice. Due to the immense strength of these 3-dimensional bonds, the reaction possesses an extremely large activation energy barrier. Conclude the kinetic behavior of the system. At room temperature, reactant particles lack the thermal energy required to overcome this massive activation energy barrier. Because the reaction rate is infinitesimally slow, the system is under kinetic control, explaining why the spontaneous transition of diamond to graphite is not observed. This identifies option C as the correct choice. The correct answer is option C. The reaction has an extremely large activation energy due to strong 3-dimensional bonding among carbon atoms in diamond.